Bill? Well, thanks, everyone. See if the up and down arrow works. Yes, okay, great. How's everyone doing today?
Good.
Is the blood still flowing after the good meal? Stomach full?
I was looking for a hi, Bill.
So I'm William R. Benner Jr., President and CTO of Pangolin Laser Systems, but of course, most of you knew that. Tell you a little story here and about our scanners and what we're doing with them. And I always like to start the story with a little bit of history. History is important. This fellow up here on the right is Coco Montague. He's the founder of General Scanning. This fellow on the left is Pierre Brozens. He is his partner in General Scanning. In 1975, they came out with the closed loop, what was then G100 galvanometer. You see him, is that a spectral laser they're looking over?
It's a 165.
Yeah, okay. So there they are, bent over 165, and not very clear in this picture here to the right is a set of scanners. And what they were working on was this here. You see the spectral laser here, set of scanners there. This is the cover of International Research Magazine, also known as IR. So this is what they did in 1975. It was the first laser projected graphic. Later on at ILDA, you will hear about and learn about laser shows. The first laser shows that happened in 1970, put on by Ivan Dreyer. They were not using scanners. They used crinkled tubes and crumpled up tinfoil and things to make effects like that. But the first actual scanned image was made in 1975, and that's what it looked like. So when
Wait. That's what it appeared to look like.
That's correct, and Patrick knows.
No,
They tried to project on the clouds, and the clouds wouldn't cooperate. So this is actually an artist rendition of what it would have looked like. But only me and Patrick knew that. Can't get away with anything. So in 1992, Cambridge Technology at ILDA, November 1992, they presented the Cambridge Model 6800 at ILDA in New York. And so from 1975 to 92, the moving iron scanners ruled the industry. From 1992 onward, moving magnet scanners have ruled the industry. Take a look at what the difference is. The cover on the left here shows 12K graphics, and in fact, to make the graphic even more interesting, they put it through fuzzy things. Then later on, the cover on the right was done with Cambridge Model 6800 scanners, and you know that they don't have to use the fuzzy stuff anymore. You can do interesting stuff just with the scanners. So this is the difference. So in 1995, Cambridge scanners had been out for a few years. Everyone was using them. The industry was comfortable with the performance, and ILDA came out with the 30K ILDA standard, right? So there it is. Now, what's interesting, and when I say this, and Patrick questioned me on this, it says, okay, so ILDA came out with a 30K ILDA standard in 1995, and guess what other standards ILDA has come out with since then for scan speeds? None of them. So in 1995, the standard was 30K, and here we are in 2019, and the standard is 30K, right? So now here's the problem. We make software that goes all the way over there, and the scanners can go all the way over there. So there's a tension. This creates a tension among tech people like me. We want to fill that gap. And so we want to scan faster. Now what's interesting is, when I first got into this, I said, well, the scanner companies can't do it. I will call aerospace motor companies. And I pick up the phone and I say, I want to scan faster. And they say, what the hell do you mean by faster? Which is a great question. We actually have to define what we mean when we say we want to scan faster. So another way of asking that question is, why aren't you already going faster? What is the barrier to going faster? Well, this is a PDF file. Usually this is a video. I make this animation of the laser bouncing off the mirror going back and forth. It's scanning a line. And what happens is you can scan faster and faster and faster up to a point, and eventually the lines start becoming squiggly and wiggly. This is a picture that Adam Burns sent me, and he said, Bill, I got this thing, and it's starting to look like this. Do you know what causes this? I say, oh, okay, great. So great. So you can tell I'm not lying. So Adam says, do you know what's causing this? Yes, I know what's causing this. And here's another one, a picture that I took at an ILDA conference. And this is actually acceptable there's a projector manufacturer, and I was walking by, and this is what their picture looked like, and I snapped it with my iPhone, and this is perfectly acceptable performance to projector manufacturers. And you see squiggly lines, you see overshoots. Do you know what's causing this? Yes, I know what's causing this. You have taken a 30K scanner and you've tried to make it go faster. It will not go faster. And another problem with going faster, so again, I'm kind of saying, why aren't you already going faster? One of the reasons is heat inside the scanner. Here, you see, this is the point output rate from the software. This represents the temperature inside the scanner. If you operate a 30K scanner at 30K, the maximum temperature that it will experience is 100 degrees C, which is fine. It can actually take that. They're designed to do that. But if you operate a 30K scanner at only 40K, the internal temperature goes up to 232 C, which is why scanners don't last. Chinese scanners, they just stop working. I wonder why. That's why. They're trying to push them too fast. Because this is the actual picture of the heat inside the scanner. It's not an artificial rendition. It's from computer software that does thermal analysis. The wire is here in the center, and the wire heats the magnet. Magnets hate heat, and there's no great pathway for the heat to get out of this thing. So there's a thermal limitation. So how did we solve this problem? For one thing, we have made the rotor stiffer. This is the rotor of everyone else's scanner. And you'll notice that this part here is a shaft end. This part here grabs only a little bit of the magnet. You notice that we grab a whole lot more of the magnet. The typical competitor's rotor, this is like a cap that they put on the magnet. It looks like the hat Tim Walsh is wearing right now. Good gust of wind and that thing is gone. Whereas we grab a 1/4 of an inch of the magnet. And so we also create this back support on the mirror so that it can sit here very securely, just like I'm sitting in this chair, whereas everybody else does what I call the bar stool approach. And it is ironic that bar stools are in bars, is exactly where you need support, because if you've been drinking, you're going to fall off the damn bar stool. So that's a little bit ironic. So this is how we create a stator. We put wires here, here, here. They're buried in slots. The heat can come right off the wire. It does not go into the magnet. This picture represents the heat of a conventional scanner when it's running at its thermal limit. The picture on the right is the temperature inside our scanner doing exactly the same job. So we tried to come up with a kind of moniker, a slogan, to describe what it is that we had accomplished. We made the rotor stronger. We made the magnetic design of the stator cooler, and when you put these two together, stronger plus cooler equals faster. So we said stronger, cooler, faster. So we have a couple of scanners that do this. One is our compact 506. This is the size of the tip of my finger. And it's a real game changer for certain applications. Here you have the compact 506 with a 10 millimeter mirror. Here you have our competitor scanner, which this is a typical scanner that they'd be delivering for 10 millimeters. Our scanner weighs 13 grams. You can see on the scale, theirs weighs a whole lot more. I like to walk around, Patrick. But you know, what you could do for me is that water in the back? Thank you, that would be very helpful. So we also have this Saturn scanners, which are higher performance. They offer the highest performance in industry, 3 to 4 times industry standard scan speed. And you'll notice that I wrote not available to everyone. And what I mean by that is we are production bound, just like Tesla, meaning that there are more people who want our products than we can produce. And so we have to pick and choose who gets them. And there's people in line for a really long time. Sometimes Greg gets in line for half a year before he gets them, but he gets them. So the point is that we need to figure out who gets them, when they get them, stuff like that. So if you're interested, come up to me and we will figure out what needs to be done to have that happen. So now let's see what we're doing here. So this graphic was produced by Prismatic Magic, one of our customers. And you can see lots of little teeny tiny details and stuff like that. And so this is kind of what's possible today with our scanners. So how do you drive them? We have a digital servo driver that is based on floating point, has built-in software tools. It's fully customizable by software, and so it's future-proof. Just the other day, Greg Makoff's colleague called me and said, Bill, we're having this problem. We've got this installation. This is happening. Can you help me? And I thought about it, and I said, I'll tell you what. You do an experiment, and I'll do an experiment because I want to prove what is happening. And he did the experiment, reported back to me, and said, yep, okay, looks like that's happening. So wrote the software 2 days later. I said, got a solution for you. So this is my car, Tesla Model X. This is my iPhone. What's in common with them, aside from they're both red? They both operate on software. They're both being updated all the time. In an age of cars that update themselves and swiping right, doesn't it make sense that other products should be like this? So we started seeing in magazines before we really got into this business. And you had to look no further than a magazine to see self-driving cars are coming. 3D printers are coming. Gosh, they sure are going to need some inexpensive scanners, and lots of them. Is anybody going to step up to this? Well, we did. Wayne Gretzky, one of the most famous hockey players of all times, reporters would come up to him and say, how is it that you're so much better than everybody else? And he famously said, I don't skate to where the puck has been, I skate to where the puck is going to be. We knew where the puck was going to be. We didn't have to have clairvoyance. All you have to do is open up a magazine and see these are the products that are coming. So we purposely built Scanner to do this up, kind of before that happened. And I just love this because some of our cars are used, or some of our scanners are used in self-driving cars. So I did this presentation, not this very presentation, but a presentation for ILDA 2013 in Holland, Germany. And so many of you would be wondering, what's new? What have we done since then? Well, in 2013, we had only one compact 506. Now we have, it's the same scanner, but we have a whole array of products all the way up to 10 millimeters. And not too far from here, at the EDC conference, Hugo Bunk is, and I'm not sure, do you know how many projectors he got on that show, Justin?
I think there's around 70 out of the...
Yeah, he's got 70 projectors there. Every single one of them running compact 506, many of them running compact 506 with 8 millimeter mirrors at 24K. So this is what we're able to deliver. And you can see my business card there. It's not just because I'm so proud of it. And the guy on the business card looks pretty cool. That's not the reason. But just to show you the size of these things. It's tiny. And another thing that we have done since 2013 is built out our line of Saturn scanners. They go all the way up to 10 millimeters now. And so think about this. In 1992, when Cambridge released the 6800, and since all Chinese scanners are based on copies of the original Cambridge Model 6800, that could do 30K at 8 degrees, right? With our 3 millimeter scanners, we could do 30K. We could do 30K at 32 degrees. We can do 30K at 8 degrees with 10 millimeter mirrors, with gigantic 10 millimeter mirrors. So it's pretty astounding. So what's new with the Mach DSP servo driver? Well, recently we have implemented a direct digital connection from FB4 to the Mach DSP. So it means that the artware, the content, remains in the digital domain all the way from the computer to the scanner. And it remains there, and it makes it gives you higher resolution graphics and also less noise, and makes it harder, still not impossible, but harder to commit kind of software piracy. Because in the past, we'd talk about this and people say, well, I'll just get out a pair of clip leads and clip onto it and I'll suck it off with an ADAT or something like that. And so it's going to take more work now. Still not impossible, but it'll take more work. And we also have developed recently, it's not quite ready yet, but an H-bridge power amplifier that basically doubles the scan angle that we already had. Now remember, our Saturn 1 with 3 millimeters would already go 30K at 32 degrees. So it means we can go more than 60 degrees at 30K of the original ILDA 12K test pattern, which should be astounding. And I'll wait until later. Don't get up just yet. saved the standing ovation. But yes, and even the gigantic 10 millimeter beam scanners that we can get performance in excess of what the industry standard performance is, which is 30K at 8 degrees. So where do you learn about these things? ScannerMAX.com, and if you go up to the top, you'll see a section there that says, can your scanner do this? Because sometimes people write to us all the time with universities, this, that guy, Intel, whatever, they'll write to us and say, we want to do that. Could your scanner do this? And so we put a section on our website that says, can your scanner do this? Where you will find reports that we have made where each time somebody says, can your scanner do this? We say, gosh, I don't know. We'll try it. And so we try it, and we make a report based on what we found. And one of the things you'll find up there is a video showing our system doing 72 degrees by 92 degrees, which our client, after we demonstrated we could do that, customer has bought many of these systems for laser projection application. It's not laser light shows, but it's what's called OLT, optical layout templates. So of course, you're all sitting here, you thought you were going to come for another presentation, and so there is just one more thing. Patrick got it. So remember this one. What was done in 1975? And we take a look at the kind of thing we're doing today, right? And this is actually even spicier than what we're really doing today, because Justin overlaid a couple other graphics on it. So it's not even this cool today. But if we compare this, what was done in 1975 to what's being done today, it's like, let's see. In 1975, we could do 2 letters, we could do an I and an R, and now we can do more letters, and we could change the color, right? So, but still, you know what's funny is because I've been doing this so long, when I look at this, what I really see is this. It's like the same damn thing. It's like we've been doing the same damn thing for 1975. It's like almost nothing has changed. And so in 1992, Patrick and I, when we were coming out with a Laser Show Designer for Windows platform, we were migrating from Amiga, and we said, how can we make this better? You know, so we came up with lots of ideas, including 6-channel color, but we said, wouldn't it be nice to actually control the beam diameter, right? So we can control the X, the Y, the Z, the color. Wouldn't it also be nice to be able to control the beam diameter? And so we came up with a specification called the beam brush specification that we put out there into the world, and we had 3 test frames that said, this is kind of some of the stuff that we do. This is an idea, this is kind of the nature of what we do if we had such a thing. And so now, the whole thing was based on naive thinking, because back then, and I run into many people that have the same belief, that the idea is the most important contribution that they give to the world. It's like, I come up with this bright idea, now shower me with money, world. And hadn't happened to me yet. Hadn't happened to Mark Zuckerberg. Not only did he come up with the idea, but he had to do a whole bunch of work. He's still working in the company. So back then we had this naive thing that if we just put this idea out there, that surely somebody would do this thing. After all, the idea is the hardest thing. It's not actually doing the thing. And Patrick came up with a brilliant name, Beam Brush. Patrick should be working for Apple, I think. He comes up with great names. So what have we learned in 34 years of business? Our thinking has evolved. Now we know that idea is not the important thing. Ideas are cheap. Execution is expensive. In our pursuit to accomplish this, we have evaluated many different types of deformable mirrors. Liquid lenses from Optotune. Even, you might remember this one, Greg, an AOM that runs in the Ramannath regime, which sounds like it expands the beam, but it creates nice little circles. And oh, by the way, the red, the green, and the blue all diverge different. But so yeah, and heck, I have 5 separate patents on beam brush devices. But what we've learned is that all devices have some kind of problem, whether that problem is bandwidth, or size or power handling capability or cost. It's got to be able to afford the damn thing. Or artifacts. And I looked and I scoured, I tried to find some pictures of this because Greg and I did many of these experiments at his thing. And what we find is that look, at Laser Light Show, we live in the square wave land. We want to go from here to there. And so we would put signals into these various devices. They go from here to there, and they go doing, and then we go back down to zero, and they go doing. What's happening, Dirk? Am I exceeding my time?
No, not yet.
Okay, because I've got a little bit more. So to give you an example of one of the problems, in our fourth generation device, if you take a look on YouTube and you YouTube Pangolin beam brush, you will see this video that's been there for more than 10 years. And you will see a device that works beautifully and actually doesn't have projection artifacts. The problem with this one was it was bigger than this cup at about the size of a cup. And the problem is modern laser projectors can't fit a coffee cup inside. You cannot angle a coffee cup in any dimension and fit that in that projector. So why is this so hard? Why hasn't anyone done it before? Another way of asking that question is, what would make the perfect beam brush device? Well, obviously, it's got to be reasonable cost, compact, can't have any projection artifacts, operate at the speed of scanning, should provide readback capability, and give you the ability to expand the beam. So here's our fifth generation device, and here's how it works, and this is what it looks like. The beam comes here just under the Y scanner, skates just under the X mirror, passes through two lenses that Ryan didn't visualize here, off a retroreflector, back onto the X mirror, to the Y mirror, and finally out the door. And so here was what it looks like in a projector. Hope many of you have seen this. Here's what it looks like from the front. So you can see this hole here. The beam comes just around here, goes through the beam brush device, and finally onto the XY scanners, almost just like it would in a regular laser projector. So does this meet our criteria? Is it reasonable cost? Well, Justin hadn't put a cost on it yet, but it's a scanner, a couple of mirrors, a couple of lenses. So I'll let you argue with Justin about how much of that's worth. It's compact, as you can see, no projection artifacts, as you've seen. It operates at the speed of scanner because it uses a scanner. It definitely provides feedback as to where it is in the field. Large degree of divergence adjustment, up to 25 miliradians, and more. Need some way of accomplishing this, need software to actually control these things. So if we had a device that did this, this is what we would have accomplished way back in 1992. These pictures were provided me by Laser Fantasy. This is some experiments that they did, and this is how they would have used one if they had one, to create nebula and comets and the plumes on space. This is some pictures that I took of our fourth generation device, some abstracts and that sort of thing, just kind of give you some ideas, some of the things you could do with this and beyond. So we have created some software tools that allow you to control this in various ways. You can see like small, big, small, big, small, big, small, big, no overshoots in that. Abstract. And we all like these swirly balls. Wouldn't it be cool to take a swirly ball and impress brightness modulation as well as divergence modulation on it? And this thing. So I know what you're thinking. And the fact is that we're not really ready to produce this yet. 4 days ago, this didn't even exist. 4 days ago, Lyra said, hey, ILDA's in 4 days. You got that beam brush thing working yet? So yeah, we're not really ready to produce a thing, put a price on it, and that sort of thing. I think probably early to mid next year will be a good target for us to have this. And do you have anything to say about that, Justin?
Yeah, we're hoping to showcase it at ProLab Design in Frankfurt. That's where we'll really debut.
So I'm just trying to bring the industry out of 1975, because every time I look at it, it just looks like this to me. I have a book on laser scanners, and actually about halfway through my book, the beam brush device here, our fifth generation one, appears in there. It gives you a little theory of operation, so if anyone wants some more information, if you don't already have my book, I have a very small number here, and you can figure out who's going to fight over them or you can buy it on Amazon Kindle right now for $1. So thanks for joining us. So I don't have time right now for questions because Derek has already extended my time and I'm already starting to eat into David's. And so, but I will hang around here a little bit. It turns out the only time constraint we had was with Calvin. I wanted to get myself here so that Calvin get off the door, out the door, and just thanks for accommodating me.